So. Yes. Anyway, so yeah, the parking lot was empty. I guess it must be like people aren't coming in today or something. Why?
There's always a lot less people here, like on campus on Fridays.
Okay.
I don't know.
Yeah. All right. I thought I was missing. What is it?
There was not many classes.
Oh, okay. All right. Yeah, I guess. But I guess I haven't noticed that before. Anyway, there's not many people in here either. But so next week's Friday probably be totally empty, but I'll be here. So CK or KC at Kansas City, the guy, the Indian guy, he's going to teach on rheology stuff next week. He did stuff with ultra high molecular weight polyethylenes, like let's see. Well, they figured out they could make ultra high molecular weight polyethylene, molecular weight over like 2 million or something like that. So some huge chain length in the 70s, I guess. I think DSM, the Dutch chemical company, did it. Then they didn't know what to do with it because you couldn't melt it. Like you could get it above the melting point, but it was still a solid. Like it was so entangled that it was like just a mess. So you couldn't process it. So then they figured out you could do you saw it, the you went to the plant. None of you guys went to you went to it. Okay, all right, yeah. So they had that rotational molding thing. So the only way you can't extrude it because the extruder blows up. So the only way to make things with it initially was to do powder rotational molding. So you fill the powder into one of those molds. So that's how they make the truck bed liners, because it turns out that it's got incredible friction. It doesn't wear at all. Like it never wears. So basically, if you want to just dump coal or whatever, any kind of gritty dirt stuff into it, it won't wear down.
They kept talking about the coefficient of friction a lot throughout that board, like how
to
get different mixtures and whatnot.
Yeah, I think it's mainly like you get abrasion products, so like hip implants are made with it too. So because of the abrasion issue, like if you get a small, like in a hip, it's flexing all the time. You have a titanium knuckle kind of in a high density, ultra high molecular weight polyethylene cup. Because if you use any other material, eventually it makes little chips, and chips get in, make your body like builds a callus around it or something, and then they have to redo it.
So is the goal to have low friction factors for the
You don't make any particles. Like you don't make particles coming off that would get attacked. I think the friction isn't really the issue there, I don't think. Maybe they're coupled. Maybe it's coupled together. I'm not sure they know why. I mean, like maybe the chains straighten out or something. But anyway, they figured, so people calculated a long time ago, like that if you had just a covalent bond versus a metallic bond, a covalent bond is much stronger. Okay, so like you have steel and then you have plastics, and plastics are weak and steel's strong. Basically, if you could line up make something stronger than steel, and a lot lighter too. So they figured that you could take this ultra high molecular weight and put it into like I think they use like xylene at like 100 C, and you can make it kind of right at the C star concentration. So you can get the chains, and then you spin that. You spin it into something that precipitates out the polymer, like water or something. And then you can get these fibers that are ultra-oriented polyethylene. So they're like high density polyethylene, like a milk jug, but they're like super strong. So they make bulletproof vests with it. And you can make like sails for the racing sail boats they use this for. So kind of a light, extremely strong bulletproof material you can make with it. That's kind of another use of it. And then what else do they use it for?
They don't like those like race cars and whatnot, or like they use real is called not, and so there might be like something else or F1, something like that.
For what, the strength or something like composite?
They're like their wings and whatnot.
Yeah, they probably use it for reinforcing plastic. But then the like coal chutes and things like where you have abrasion resistance, they're all made from this stuff. So it's better than metal for abrasion resistance. So they just use it. So it's used for those reasons. Anyway, so he did a study in India where you take that stuff. So the high density is kind of weak and this stuff's super strong. So the idea is like you could mix a little bit of ultra high molecular weight into the high density and make increased strength. So he did a lot of rheology to do that. It's like rheological breakup of this stuff. So that'll be the homework next week. I'll do that one of those papers. He has like 2 papers on that.
Would you consider putting that homework till after spring break? Signing
Yeah.
those?
Yeah, you can turn it in after spring break. Like I'll do it on Friday, but you can turn it in like,
Maybe we can put it on this. I really don't know on the spring break.
yeah, so just do like the next week after spring break, like Tuesday or whenever you want. Doesn't matter. But so you don't have to work on it during spring break.
Okay.
But it'll be there.
Tuesday, the 19th or Tuesday, the 22nd?
Not during spring break.
Yeah, spring break is the 9th to the 15th, so it'd be like,
Yeah, the 19th. Yeah. I mean, if it ends up being a problem, just let me know. I don't expect you to work over spring break. So if it ends up like you can't do it, let me know. We'll just figure it out. But for now, like that, whatever that 19th. All right, so anyway, this week's is on this, so it's got something to do with the scaling models. So this guy, Schultz and Lang are at this place, Leibniz Institute of Polymer Forschung Research in Germany, something or other, in Dresden. So after when the East and the West Germany merged, reunified, the Leibniz Institute for Dresden. So Dresden was East Germany. And it's a place that got like firebombed in the war. And it was hot enough in the city to melt the train station. Like literally the steel was melted, you know. And then this is where Slaughterhouse 5, the book Kurt Vonnegut takes place. Like they took the prisoners, US prisoners of war, and they made them work in the slaughterhouses. Anyway, but the slaughterhouses had these underground chambers to keep the meat cold. So in that book, like they torched the city. I mean, it's total like an atom bomb, worse than an atom bomb. So not radioactive, but worse than an atom bomb because the area covered was much larger. Like the British claimed that they didn't call it a war crime because the British claimed that it was one of the first times they used napalm and they didn't know that like how much to use. So they used like 6 times what you would need to like torch a city. So basically they melted the entire city and the people in it, you know. And it was originally it was the cultural capital of Germany. You know, it was kind of like Kyoto in Japan, like all their art was there, palaces and like museums. So anyway, it was kind of like torching their heart, essentially, you know. It was a brutal thing. But on the other hand, the Germans did almost the same thing to Bristol, England. If you go there, they still have like rail car tracks sticking up in the air and stuff like that, you know. So
During World War I and II.
two, yeah, that World War I, they didn't have that kind of ability to mass annihilate. Yeah, they extended for a long time in trench warfare and they used nerve gas, but the building still stood, you know, after. So anyway, if you go to the train station in Dresden and look up the ceiling, there's still like burn marks in parts of it. You can see where, yes, it's still like left over. Then the palace, IBM in the 90s. So they had the palace was just in ruins and it was a famous building. And they went in and they logged every piece of it and they took pictures, 3D pictures of it. And on computers, they reassembled the palace, you know, and they were all labeled. So they actually rebuilt this palace that way using a computer simulation of how to put each piece back into it, you know. So it's kind of an interesting thing to see. But so after reunification, so there was Mainz is the Polymer Center in Mainz, Germany, which is like kind of near Frankfurt. You know, so the Main River goes from Frankfurt to Mainz, and along that way is all the chemical industry, like the BASF is that was originally the Bavarian, whatever portion place, you know, so. Anyway, that was the largest chemical plant in the world, and they split it up after the war. So basically that's like Chemical City, you know, and polymers are like kind of right there. So that's like the research center for polymers. And then after the reunification, they wanted to put some of these Fraunhofer centers into East Germany to kind of pick them up a little bit. So one of them was this Dresden Polymer Research Center. So that's where these guys are. So it's kind of the people are different. I mean, maybe they're more of the same now, but after first reunification, they were quite a bit different. Like they were, you know, they had Stasi and stuff, and everybody was kind of an agent, so you couldn't trust anybody. So you'd walk down the street and people would go to the other side, like weird things would happen. It wasn't a normal place to be, you know. There's some legacy of that. It's gradually washing out. Basically, you can still see some of these like communist kind of apartment buildings, like with no style to them at all, like lined up A, B, C, D, whatever. So anyway, so it's kind of a funny place. Anyway, these people are there and they're doing this computer simulation, which they don't talk, they say like all the simulations in this paper, and they use this thing called lemonade something. So, which is a Monte Carlo process. It's in this paper at the beginning somewhere. Simulations using lemonade graphical process. Those are graphic units on a PC, and use them, they can run faster. So you run the, so that thing needs lattice-based extensional Monte Carlo algorithm and development environment. But if you Google that, it doesn't come up anywhere. Finally, you can find out that the this bond fluctuation model you can find, right? That's kind of this, and that's by Kurt Kramer, who's like a guy at Mainz, like one of the guys in Frankfurt, you know, that anyway. So, and then I guess one of these people was probably either worked with him or was a student, and then ended up going to the Dresden place. So anyway, Monte Carlo means that you're going to make something change. Here's bond rotation. And then you got to calculate the energy of the whole system. If the energy goes down, you accept that change. If the energy goes up, you kind of flip a coin and see if you're going to accept it or not, based on the temperature and the energy difference that it goes. Right, so you have kind of a temperature weighted rolling the dice. So you can accept bad things sometimes. It allows it to kind of go through energy barriers, like go over a hump into wherever the minimum energy is going to be. So that's what they're doing. They're using that kind of simulation method. That this is their own. So anyway, this lemonade thing, like you Google it, you can't find it. And basically, it's from their place. It's like the Leibniz Institute, their simulation software. So that's why they're using that. Otherwise, you'd use something like LAMPS that also has bond fluctuation stuff in it. That can do bond rotation. So I don't know what the difference is. And you do Monte Carlo. So basically, most people would just use LAMPS for this same deal thing. Anyway, because it's got a huge database you can use. But anyway, they're using this thing for whatever reason. Anyway, so they select that data from that simulation in the other paper, and the other paper is kind of more comprehensive. Let's see. They also synthesize the polymers. Like they synthesize these swollen networks, and they also simulate them. So they do both in this paper. In the paper we're looking at, they're just doing a reanalysis of those simulations that they already did. So the advantage of the simulation, you can go in and you can like tag. So you already have the thing made. You have this structure. You can say like, make the crosslink sites red. You know, and then all the crosslink sites will be red or whatever, you know, so you can go back in, you can look at individual chains. The other paper is about the individual chains. You can look at the whole lattice network that you're making. You can look at the crosslink sites, crosslink molecules, some bigger thing. You can look at whatever, right? So anyway, the polymerization that they do and the simulation they do is this called the A-B. So they do like A units can only bond with B units. They're all tetrafunctional, so 4 bond things. And then it's always going to be blue-red wherever they bond. Right, so they'll make this kind of network of things. Then he goes back in and he's going to say, like, I can make the contrast only of red or only of blue or I can make the whole thing, look at the whole thing. We can mix and match what he does. And to analyze it, he takes that structure and he does a Fourier transform of it. So he goes and gets a scattering pattern from it. So he's going to take, so he goes through he goes through the correlation function thing, but what they do, let's see right here. So this is a Fourier transform of the structure he has. So he has a structure, every atom has a position R, right? And if you do the vector product ends up with a scalar. So Q dot R gives you a scalar of the values times the cosine of the angle between the two. Right, so that's like a directional averaging of the thing. So he does that, and then you're going to sum over all the possible R's in the system, and then square that thing. Take the absolute value. So it's going to be a complex number because it's going to I here. To square it to get a real number, and that's what the scattered intensity is. So this would be the amplitude, which is the complex number. So you can have constructive, destructive interference. Once you square it, you just have an intensity. They can only measure one number. You can't measure a complex number. Right, so you get the square of the amplitude. Anyway, so you don't really need to know that. I'm gonna go through scattering like in 2 weeks, like after break. So this stuff's in here and it's a main part of the paper, but I'm skimming over it to try to let you know. So hopefully we can just look at the curves like intensity versus Q, except for one thing. Like he does this. Okay, so he says he has like the A units, so the red ones and the blue ones. So like this would be like the amplitude of the scattering from the red ones, amplitude of the scattering from the blue ones. And then he weights them by whatever contrast he wants to make. Like he can make this a large for the red ones and small for the blue ones, or whatever he wants. And then he takes that amplitude and squares it to get the intensity. And so, but this is the kind of thing you would do if you had, say you had 2 layers and one layer was red ones and one layer was blue ones, right? And they don't interpenetrate, right? So this isn't really the right way to do this thing. Like the first step he does, this isn't right. You have to go back. You have to use this. It's a lot of words at the beginning, but this is called the random phase approximation. You'd have like the scattering from one of them. The inverse, it's an inverse sum. So if one of these two is small, then the small one dominates over the large one. When 2 things are interpenetrating, the small one dominates over the large one.
Similar to like the resistance.
It's similar to a lot of things. Yeah, so it's a harmonic mean. So it's like how you average interest rates or velocity, any kind of rate averaging. This is how you do it, right? So it's when things are intermeshed. If the things are separate, so you have one layer of blue crosses, one layer of red crosses, and what he did's right. But if the 2 things are hooked together and they're also squiggly chains that are intermeshed with each other, you have to use this approach. And I'll show you, I'll derive this later on, but basically his first step is wrong. Like you can't, that isn't how you add together 2 things in scattering. So he's a simulation guy, he doesn't understand that. So this is called the random phase approximation, right? So anyway, so basically, I guess I'm just asking you to say you have a small number and a large number, and then add them together this way and see what number you get here. So you add 1 over the number plus 1 over the number, and then take 1 over that to get this thing. And versus just summing the 2 weighted like a arithmetic, and just sum the 2, like whatever you talk about for the average, right? Like this plus that divided by 2, right? So you get different numbers for it. So that's one twist to this thing right at the start.
What he's doing, clarifying, on the
Yeah.
paper, he's taking this
Linear sum.
linear stuff.
So he's getting, and these are fractions, like A and B are going to be the fractions. He's actually like taking this plus that divided by 2. Like this would be 50%, that's 50%.
And you're taking that for all, like.
That's how he gets
rotational
his,
states. So
the rotational state is how he gets the structure. So the step 1 is like, I start with this cross pattern thing, whatever he had here, and then I'm going to let the bonds rotate in it, right? And if that lowers the energy, that's great, I want that. If that raises the energy, then I do this flip the coin thing. I might take it or I might not. So I can get over an energy barrier to get somewhere else. So basically he's gonna let this thing squiggle until it finds the lowest energy that it can find. Right, and then once it reaches a constant energy, he's done and stops the simulation. Right, and the size of his box is like,
The energy would reach like, when you're triggering like the bond like that, would that be like temperature? Like,
yeah,
temperature?
KT is the rate of the bond flipping. Yeah, how fast it moves. But once if you have two things and then say you rotate it here, like we saw when you have carbon, you rotate around that bond. Well, there's a potential plot, right? Goes up and down. So when the two side groups are over each other, there's a high energy. And then when the side groups are catty corner, there's a low energy. Right, so it's like a 3 toggle switch of energy. So every bond rotation is going to be a 3 toggle switch. So you let them randomly toggle, basically. You're going to go to positions that are in between too, so that the thing can do any shape that it wants to do, potentially, with the flipping the coin. But normally you're going to say like it goes to the toggle switch positions. Right, so yeah, then you calculate the whole energy. It's a 720 cubed box. These are 20 of these kind of monomer units, whatever, like kind of an arm length unit. So it's going to be 720 pluses across the thing in 3D, which he thinks is big enough to do this. All right. So anyway, yeah, so that's the simulation that we aren't really looking at that. Like we're just looking at the result. So, and then the result is he's going to have a position of every atom in the thing. It's going to be R, or every Kuhn unit in the thing is going to be position R. So that's a vector. It's like X, Y, Z. And then Q is also a vector. There's QX, UX. You do the dot product. So you end up with a magnitude times a cosine. So if they're going in the same direction, it's a Q times R. If they're going in 90 degrees, it's 0. Right? So it's like a cosine function of the angle between the things. So both vectors, how does a projection of one on the other go? And you're going to sum over, you're going to do exponential, times complex number, and then so this is basically a sine wave. Like the exponential IQ is like sine of Q dot R times 2 pi, and then minus I times cosine. So it's like a wave that's got like an electric field and a magnetic field. So there's an imaginary part, like magnetic field, and the part that you can measure the electric field. This is kind of like, it's an electromagnetic wave. So you got complex, that's just a complex wave function. So the e to the IQR equals sine of 2 pi QR minus I times cosine of 2R. So this is just a sine function. So you're saying that you have this, you're going to sum up these sine waves, you're going to square them, you're going to get it for one value of Q, then you're going to sum that thing. Anyway, we can talk about Fourier transform later on. Basically, this is just a function used to get the intensity. It's a Fourier transform of the R space thing that we have. So anyway, so then he talks about these business correlation functions. This is a little bit off track. I think he did this to get so he could justify the other equations he uses. The first one's, this is the polymer chain scattering equation by Debye, which is for a Gaussian chain. So this stuff's in good solvent. This equation isn't appropriate. This equation isn't appropriate, period. And then it's got, it's a Gaussian, because of the 2 here, it's a Gaussian also. So neither one of these really apply to the system. So he's got a lot of scattering problems in this paper. But this is all right, we'll go through these functions later on and kind of critique them. But basically they're commonly used, but all of them are basically not appropriate, what he's doing here. But nonetheless, he gets good fits from it. So he's happy with that. This is the function scattering from a sphere. Like if you have perfect spheres, and he uses that. I don't think he actually uses that because all he uses is Gounod's law, like whatever that is. He ends up just using this, which is Gounod's law, like a Gaussian. It's a Q squared, so it's a Gaussian about 0, Q 0. So it's just a bell-shaped curve about 0. And the width of that is going to be like usually the radius of gyration squared, but here he's talking about a correlation length squared. So this is just going to be a knee, and in his log, he has log plots. So it's just going to be like a knee in the plots. Like you have a knee here. So here the dashed line is this Gurnier's law on a log plot. This would be what a bell-shaped curve looks like when you plot log. Looks like a knee, right? So it matches up with some component from his simulation. So he says that he has the chains. So there's this bond rotation thing that causes everything to fluctuate. And then there's the crosslink points that he says are kind of fixed, right? So he says that the fixed crosslink points give rise to this part of scattering that he can separate because he can look at the dynamic part, the part that's kind of shaking with KT, and the kind of static part that isn't really shaking with KT. I haven't seen this before. It's kind of nutty, but basically that's one of the themes of this paper. Gives two correlation links. One is this kind of fit to the data, and the other is a fit to something that he generates from the simulation that he says isn't moving. So he's pretty interested in this concept. So he has a nice graphic that could have gone into like nature or something like this, except it doesn't. Anyway, so this is a slice through his network. He slices the network. Then these are the chains, and there's crosslink points in here. I guess he calls them glass spheres. And then those, if you look at, this is a plot of density across that slice through the network, and he finds out there's peaks in it, and the peaks correspond to the crosslink sites. So he's saying that the chains, because it's a tetrafunctional, there's more chain at the crosslink site than there is at other places. Which anyway, so that's one of the things he brings out in this. All right, so he gets these curves, he gets these scattering curves somehow, and he's going to fit with either this exponential, just the Gurnier's law, to get kind of an RG for the things that are static, he says. And then he's going to fit with, I think he uses the Debye function to do these fits. So the kind of the mother of all polymer scattering functions, this thing. So this is for a Gaussian chain, an isolated Gaussian chain, not in a mixture. So he's got a network where they're pretty crowded around crosslink sites. So some problems with applying this. They aren't Gaussian, they're a good solvent. So this equation isn't appropriate, and it's not really an isolated chain. So they're hooked together at crosslink points, right? So anyway, nonetheless, he can get a good fit, and he's happy with that. So like the black lines are fits, they look okay, right? So, and then you can get a size from that, which you could have just done Gurnier's law here similarly and gotten this correlation size to the thing. And he goes up in C star. So he has half a C star, so dilute, right? And in that condition, the network is the hollow ones and the free polymer. So this free polymer is the solid ones. So free polymer versus the network. And then so normally as the concentration goes up, so he has 6 times C star, like the bottom one, that should be 6 times higher. Like where these match, that should be 6 times, should be I by phi. It should be 6 times higher than this one if you just plot I. So he's made it lower, so it's kind of misleading a little bit. I mean, he made it so that they didn't overlap with each other, but in doing that, it's the opposite of what the actual intensity would have been. But he's going just like 1 decade down or something for each one of them. And then, so anyway, the actual intensity values here can't be compared between the curves, right? Otherwise, this high Q part would match for I by phi. The high Q part here would be on top of each other. So he increases the concentration, he gets the screening thing that we're talking about. So this is the concentration blob size, that knee part, right? And 2 pi over that Q value where it goes over is the size of that thing. And he gets a different knee for the free chains and one for the network chain. So they're smaller when they're in a network because they're in a network. So that because they're kind of more crowded in the network, I guess. So you get concentration screening even when you're at half the overlap concentration. So if you just take a polystyrene network and then throw it into toluene, it'll swell up to some fixed value, right? And that's a compromise between the elastic energy of stretching the chains and the osmotic energy of trying to pull in as much solvent to dilute it as much as you could. it wants to dilute it as much as it can compared to pure solvent. So that's the osmotic pressure, but it doesn't want to stretch out because it's an elastic band. Right, so the elastic part's pulling back in. So that gives you this Flory-Reiner equation for swelling of rubbers. And it's got to do with the cross-link, molecular weight between cross-links. 1 over this V2 is called the swelling ratio, how big it swells. That's a volume fraction of polymer. Chi parameter, molar volume of the solvent, this molar volume of the polymer, enzyme monomer, or the Kuhn length molecular weight. So it's an equation that describes, so you can use this to measure molecular weight between, say you make a rubber, just throw sulfur into butadiene rubber, mix it up, and then it cures. And what's the molecular weight between cross-links? Well, you don't know because it's a random process, but you can swell it in toluene, and then you can find this MC from that molecular weight between cross-links. And also, if you know the molecular weight between cross-links, say it was N-link, like in this case, then you can measure the chi parameter. And then Flory's book, on these pages, he goes through that in depth about how you get this equilibrium swelling to measure the chi parameter. And then later on, de Gennes came up with this idea that when it's not, so the Flory's basis is on a theta solvent, so they're Gaussian chains, right? But in reality, if you put them into a good solvent, they're C star chains. So basically, de Gennes came up with this idea that they were, you could say that this is a C star coil. The amount it swells is going to be the concentration within the coil at equilibrium at C star. So the whole thing will swell to C star. Then the crosslink site's going to be kind of joining the C star coils together. Right, so you can figure out what the swelling ratio is from that. So this is the model he's using here. This is kind of like the modern models to use. Both models are still used, but basically this is the kind of more modern model. This idea that you have a C star chain hooked together, it'll swell to equilibrium as much as it can to reach this state. Also, it's interesting, like he's using his cartoon that he shows the same as a cartoon in de Gennes' book. Like this, these two things are exactly what he has, except he didn't put the wiggliness in. So you can look at that if you want. Anyway, so that means you can measure this so in a simulation he can swell it to any degree that he wants. So he can put in whatever volume fraction he wants. So he can just tune this thing to anything he wants. He has a fixed molecular weight, so he's effectively changing the chi parameter when he goes through this thing. I mean, if you think about it that way. But he can just do whatever he wants as a computer simulation. So he just puts any concentration he wants. This is the result he gets, which it seems pretty reasonable result. I mean, I don't like the functions he's using, but the result's good. So from that, he gets this correlation length, and he plots the correlation length. So this is his static, and these are his dynamic components to the thing. And the bottom one here is the network, and the top one's the free chain. Right, so you can get the dependence of the correlation length as a function of the fraction. Let's see, the fraction at preparation, and then so the red one is the fit color laws alpha is summarized in table 1. So you expect this to be this set minus 3/4. Like in the class we went through, like equilibrium swelling, you get this thing with this blob size would go with concentration of the minus 3/4. That's the expected result. Right? And he gets that for the free chains, which is comforting. Like he gets that 0.74 for the solid, the all chains one. Right. So basically he gets that behavior. When he has the network things, he gets a lower slope to the thing. But then when the concentration gets high enough, so you're overlapping so that there's no difference at some point, right? When you get to a high enough concentration, then you're swelling like within the network junction. So you can't even see the network junctions anymore. You only see like the coil that's within the network junctions. And at that point, the polymer that's free and the polymer in the network are the same thing. Right. So kind of the cutoff is like maybe the blue one or something. So that's like 3 times 3 times phi star, you can't see the network anymore. And then the free chains and the network chains are the same. They show the same screen. And that data that comes from that is that they match up out here. So the green ones tail over and go on to this minus 3/4 slope that we got when we derived it in class for the concentration blob thing. So that kind of makes sense. You know, the blue one is for his imaginary whatever, the static thing. The blue one just does weird stuff. So, I mean, it's hard to tell if the blue one exists and you know, it basically does weird stuff. What else is in here? It goes through a lot of the dynamics things. Oh, and this is where he increases the molecular weight in the network, and basically it goes towards the minus 3/4 slope that's predicted, right? So when you get to a network that's just almost like free chains, is so loosely cross-linked, then it acts like free chains. It's like, that's kind of good too. I mean, that's how you'd expect it to behave. So what's that picture? That's kind of what he's got here, I think. Oh, then he gets, all right, then he gets into this stuff. So he ends up with this, not that thing, this thing. This is the intensity ratio of, let's see, what is this? G and F. F is his network, his fractal scaling network thing, and G is a Gunier for his static thing. So he has a static over the network thing. So those are the extrapolated intensities to zero angle of either this thing. So for the networks, like that number here, or the number for his weird crosslink type things, like these things that are steep, just Gunier's law. So that number. So the ratio between like this blue number and that purple number. So he has, I think he has G over F. So it's a purple over the blue, I think, isn't it? Let's see. This is stuff he's kind of invented here. Yeah, G over F. So it should be a number smaller than 1 by that plot. So it's generally smaller than 1. Then this is a function that he gets. So he has the scaling relationship for the chain, like the free chains, which he gives somewhere in here. Let's see, it's kind of right in here somewhere. And we went through this in class, this business of this scaling relationship, this 3 nu minus 1, and a nu minus 1/2 he gets in here somehow. So he gets that ratio is going to be, you can calculate what the slope of that thing should be from the scaling laws, and he gets agreement with it down to some molecular weight. Let's see. So nu is 1 over df. So this is just the density. N3 nu minus 1 is the density. So this should drop. So dropping this increases the molecular weight. So molecular weight goes backwards here. So this is where he reaches large chains there and small chains over here. So this is anyway, it asks you to kind of look at this a little bit and figure out what he's doing there. I mean, I can kind of vaguely see what he's doing, but so why don't I go through this thing? So this gives a little bit of background. If you want to look, if you can look in the books and see, this is extensively derived in the Thori chapter, if you want to see it. Then this is loosely derived in the gens chapter. It's at the end of it. They're both at the end of their books. You know, so it's almost like the gens wanted to put at the end of his book because Thori put it at the end of his book type thing. So, but it's a completely different perspective. The Thori one's readable if you like to do algebra, and the gens one's not readable no matter what, probably. Like mostly it's hard to read anything he writes. I mean, you have to spend a lot of time. Every equation, you're like, where did that come from? That thing, he doesn't tell you. So Anyway, but basically, usually it's kind of worth the effort to do that, but not necessarily. But, and then then it just says to comment on that, like do it, just figure out how that works, like how wrong he is when he adds two things together the way he did it. Like comment, work out how the resulting intensity would differ for low and high Q, like take the values off his plot. Just figure out how that would be different for a couple points. And then this is what, so we did the minus 3/4 in class, do the derivation from class, and then his data shows that behavior at high molecular weight between cross links, and it also for the chains that aren't in a network. And then the ones that aren't in a network, that behavior is being perturbed by the network confinement, I guess, something like that. Different scattering, the freestyles. So that's just that they're confined, basically. That's why they're different. They're confined chains. And then this is the thing. Figure 8 is just that thing of oops. See. Yeah. Figure 8. It's gonna stick in here. Be an operator error. But 5, 6, 7, 8. So yeah, this is just as he increases the molecular weight, it goes to the minus 3/4. That's what figure 8 with molecular weight. That's because it chains when it gets to be a looser network, then it can't anymore. So you can, in fact, like so it's kind of a limit to what you can do. So you have a chain. So say it's 2,000 grams per mole chains, and you want to end link them. So you have some functional group that will condense with another one. So, I mean, you have to look at the probability of the two end links that are randomly squiggling around a polymer melt would find each other. Right, which, yeah.
When you're saying the chains become loose, they become undefined.
Yeah, because there's such a long distance between crosslink sites that they're just like, it's as if they're just a free chain. Yeah, and if you tighten that up, so if you have really short chains, like 100 grams per mole between the monomer or oligomer you're using to make the network, it reacts right away. Like the ends can find each other. There's so many of them, right? But if you try to make a network with things that are large, like he's doing here, in the simulation you can do it. But if you're doing it in actual experiment, like the ends you'll never get it to work. Like you make kind of a sol thing, like a viscous, gooey thing, but not a network. Because they can't find each other. There's not enough end groups to find each other statistically. Right. So he's making things that you can't make, like with a computer. There's a limited range of window. Like if you really do like 10 or 20 mer unit, and then it just is like a glass when you finish with it. It's like a solid glass. It's not a rubber. It's not a network really. It's just like a solid chunk. But if you get to like 100 mer units, that's about the sweet spot. I mean, you can get a nice rubber from that. If you go to like 500, all of a sudden it doesn't make it doesn't condense. Like you never get a network from it. So the thing he's doing, like he's going across a huge range of molecular weights. It's not necessarily possible to do that experimentally, like whatever he said, whatever the end part is. Some plot is just straight in this thing, not that, not that. One of these is just n. It's all concentration. Anyway, somewhere is n, but I think he goes to like, so he's freely manipulating the n, and it's not it's not exactly realistic. You know, and maybe it's good because you can do it in a simulation, you can't do it in an experiment. Let's see what that plot is, but this is n, but it's an n function, right? But anyway, so anyway, that's just, oh, it's figure 8. That's what I was searching for, but figure 10, figure 9, figure 8, n. Yeah, so it's in a log scale. There's got, oh, this isn't, and it, oh, I see n's up here, right? So it's hard to do that kind of manipulation in the experimentally, but then he shows this thing, figure 9 is this graphic, like his premier graphic thing, showing the idea that you have these density fluctuations, like a higher density at the crosslink sites, that kind of business. Then this is the 3 nu minus 1 is the how you calculate the concentration of the density of the polymer chain. Nu would be 1 over the fractal dimension. And then he uses that function and then gets this weird axis. Like this thing here somewhere. That's 3 nu minus 1. I use just 3 nu minus 1 for this. That's just the density. That's the density function. And he's going versus the that static versus the dynamic 0 intensity scattering. So I don't know, just kind of figure out, see if you can figure out what he's doing there.
I just have a question.
Yeah.
We were talking about how like the unconfined chains, like, and then loose end and whatnot,
Mhm.
is he able to? I'm kind of like just trying to correlate with like how his data. He got good data, but he used equations that he shouldn't have used because they're not isolated.
I mean, all he's getting out of it, if you look, is just the size, right? So he could have just used Grenier's law. It doesn't matter what equation you use. Because all he's doing is, so all those equations are going to tail over. See, they all tail over at low Q to Grenier's law, like this knee thing. He even mentions that in there. So basically, if he had just done Grenier's law fits to those things, he would have gotten the same, roughly the same answer. Like this is Grenier's law, right? And then this other thing is this, I think he's using the divide function. So you can see, like, if you just took Grenier's law and marched it up there, it would match with that part of it, like this end of it, and you would get the same size. So as long as you have a knee part to your curve, you're going to get some size of it. That's the only part of the curve he's using. And then, I mean, he also says like it's the 5/3 slope out in the high end, like it's a good solvent chain, just to verify that that's what he's looking at. But the knee part is the only part he uses for numbers. But in all these plots, all the correlation lengths are just the knee part. So he could have just used Grenier's law and gotten this. Then all these functions revert to Grenier's law at low Q, in some form or another. Right? So that's kind of the picture of the thing is you're going to have like these power law regions and you have these Grenier regions and they're going to be hooked together somehow. So that's pretty much a picture of a lot of this kind of scattering from disordered materials. I mean, there can be more than one knee in it, right? So you can have more than one Grenier's law of it. So yeah, you're right. I mean, yeah, I said he's using the wrong functions, yet they seem to fit and he gets a number out of it. But basically that doesn't mean this end of the curve is always going to be the same. So it maybe doesn't matter that much what function you use. To do his whole interpretation is just on that size. Like he has I naught and he has a size. So that's all he gets out of those fits. So whether or not it's the right function, maybe it doesn't matter. Anyway, he gets good trends out of it. It follows the minus 3/4 concentration dependence. That's good. It's hard to get simulations to work out that you get something that looks real, you know. I mean, it's not that easy to do that. So it's good that he got the result that he got. So it makes you kind of believe the simulations. But again, it's his home brewed simulation package that I think isn't published. So you don't really have access to what the black box is that he's coming out with. So then at that point, is it really science or what is, it's not.
Verify it, you can't verify it.
Yeah, he's had a series of postdocs or something that wrote the code and messed with it. And they just feed the stuff in and get out the things, so. Yeah, you can't, there's no way to duplicate what they did. You can get their code and run it and say, yeah, it looks right. That's all you can do. So that's partly, if you use a package like lamps, then like everyone and their brother has used it for like 30 years, or 40 years even. So it's kind of like you pretty much know that it is a black box. You're not going to go in and look at they released the code, the raw code. So it is accessible if you want to, but you wouldn't really understand it, look at it. And it's going to be like tomes of code spitting out the stuff. So there's no way, you would spend like your whole career just looking at the code to verify it. So, but it's more believable if everybody uses it, at least you're on the same bus as everyone else, who's going off the cliff. But anyway, so all right, this last point though, I didn't mention this. So if you have these chains so this is an issue that he ignores. So he has a box I think it's 750 by 750. So if you have these crossing sites, then you have chains that are going off, right? And then there can be some that, like and they're allowed to rotate, so they can have some that are entangled. So his are monodispersed, right? But generally you have a crossing site and some long ones and some short ones, right? So if you put a stress on this, like those chains, the short ones are the ones that take the stress. And you can have other crossing sites. And then this is going to go off in a network in 3D. And so basically there's going to be some pathway, say, through this. It's going to be like the shortest chains are going to, they could pull on this thing. Right? Then it's going to be the shortest chains, and the rest of these don't even matter. Right? So you're going to just have like a pathway through it like that. You're not going to have all this other network. You're just going to have these long pathways that show up. Right? In other words, the short chains will straighten out first, then they're just going to find other short chains, and it's going to percolate like that across it when you pull on it, or even if you swell it. Right? So it's basically those short things are going to really like govern what's going on with the thing. So he takes just like a 750 box, right? So he's got a few chains, and then like, so he can't see that kind of phenomenon, which this thing's going to go over like microns, right? And his 750 is going to be like 0.05 micron, something like that, the box that he's using, right? So basically he can't see these larger scale things that give rise to like the modulus, like the modulus that you're trying to measure for rubber. And so there's a big problem with saying that you have a simulation of networks and you're going to predict the behavior, and you're ignoring like these kind of large scale features that happen. So that's a detrimental part of the simulation thing. So that's what this question is, just saying like, think about that. So that's about it. Yeah. I couldn't really find a paper that was exactly on the simulation, on the scaling stuff and the blobs. Like this is about the blobs, but it isn't like really focused on that exactly. It's got the equations in it. So there were some other papers that were even further from it, just mentioned it, So it's kind of like, it was a little bit hard finding a paper that was appropriate for the week for whatever I did in the lecture, but this is kind of close. It's got blobs. And this is one of the applications of blob theory, is that the Gens C-star network theory for how the swelling goes. So anyway, so you can get out of it. It's good to know about because both Flory and DeGens focused on this gel equilibrium swelling problem. So it's kind of a thing that's it's one of the books of the Bible, for polymers. So somehow, and people will kind of use it in different places. So it's good to know a little bit, take a glance at the Flory-Reiner theory and glance at the Gen C-star thing, get a feel for that and see how this guy applies it in this simulation problem. But anyway, that's about it. So I see like, we'll be back. Mm.
And 15 because I have like a doctor's appointment.
Right,
But I should be able to get like the first bit,
all right,
so
okay,
just so, I'll like send you an email once I like put it together. but-
yeah, that's okay. I mean, anybody here really like the day before, given the way things are on a normal day, you know?
You're on once, but that was because I like was so stressed out for an exam that I was fighting back, like getting sick, so.
Yeah.
I'm just like, no one wants to hear.
Yeah,
I'll probably be here.
okay,